unsaturated hydrocarbons. Okay, like we said, there are those carbons that contain at least one carbon-carbon double or triple bond. If you got a double or triple bond, okay, then you can't have as many hydrogens as is possible because a double bond takes some away. Okay, so these include alkenes, alkynes, and aromatics. So if it ends in ANE, it's all single bonds. If it ends in ENE, there is at least one double bond. If it ends in YNE, there's at least one triple bond. And aromatic means the benzene ring. We talked a little bit about benzene. We'll talk a little bit more about that too as we go on. Okay, so all alkenes have at least one carbon-carbon double bond. Alkynes have at least one carbon-carbon triple bond. Aromatic compounds are very stable. They're a cyclic compound, alternating single and double carbon bonds. Let's see what a picture of it. Okay, this is what's called a conjugated bonding system, where you're alternating single bond, double bond, single bond, double bond, single bond, double bond as it goes around the structure. And we don't have that, so it goes back to everything here. Okay, so it would be benzene would be 6 carbons, so it'd be a cyclohexane, and then it would alternate single double bond. So there's a double bond, single bond, double bond, single bond, double bond, single bond. That's what we mean by a conjugated system. Every other bond is a double bond. Every other bond is a single bond. Okay, it's very, very stable because the electron configuration that occurs with it. Okay, so this is an aromatic compound. Anything having that structure, which is common in steroids also, is what's called an aromatic compound. Okay, so both alkenes and alkynes are unsaturated. Okay, the alkene is our double bond. The alkyne is a triple bond. The simplest alkene is ethene, which would be C2H4, carbon, hydrogen, hydrogen, double bond, hydrogen, hydrogen. That's the simplest one. That's your ethene. Eth means 2, right? Like ethyl group. Ethene means it's 2 carbons, 1 double bond. Simplest alkyne is a triple bond, which is acetylene, which is actually ethyne. Carbon, triple bond, hydrogen. That's ethyne. Its common name is acetylene. Use it in welding. But the IUPAC name is ethyne. 2 carbons, 1 triple bond. Okay. So many of your biological molecules, have these double bonds or linear or cyclical conjugated systems, double bonds. It gives it a stability when you have that alternating single bond, double bond structure. Again, that's called conjugated. Okay. Fatty acids, okay, are classified as either monosaturated, has 1 double bond, or polyunsaturated, having 2 or more double bonds, or saturated, has single bonds only. Okay, so that's how we classify fatty acids. You have monosaturated fatty acids, which has 1 double bond. You can have saturated fatty acids, which have no double bonds, all single bonds. Or you can have polyunsaturated fats, which means you have got 2 or more double bonds. Okay. Vitamin A, okay, it's retinol. That's required for vision. Contains a 9 carbon, okay, 9 carbon conjugated hydrocarbon chain. So conjugated means repeating every other bond is a double bond. Okay. Vitamin K, which is required for blood clotting, contains an aromatic ring, that benzene ring, 6 carbons in a circle, and alternating single and double bonds. Okay. Here's vitamin A. That's what it looks like, retinol. Okay. You can see every other bond is a double bond, and everyone before that is a single bond. It's just called a conjugated system, and they're very stable. Okay. Vitamin K, same way, has a repeating unit. And again, here is alternating. There's an aromatic compound, alternating single and double bond. Okay. All right, so alkanes. Okay, my computer. All single bonds. Okay, the formula is CnH2n plus 2. So if there's 2 carbons, there's 6 hydrogens. N is the number of carbon atoms. If there's 3 carbons, there's 8 hydrogen atoms. An alkene with 1 double bond has the formula CnH2n because you don't have those 2 carbons on 2 hydrogens on the end anymore. An alkyne is CnHn for only 1 triple bond. If you have more than 1 double bond, this formula doesn't hold up. If you got more than 1 triple bond, that doesn't show up. So only for 1 double bond and 1 triple bond do those formulas apply. But this is ethane, again, A-N-E ending, so you know it's all single bonds. This is ethene, E-N-E bending, so you know there's a double bond. And this is ethyne, Y-N-E, which is a triple bond. So A-N-E is single bonds, E-N-E is double bonds, Y-N-E is triple bonds. Okay, you got your molecular formula and you got your condensed formulas, what they look like. Okay. The geometry and the shape of these bonds. Okay, for ethane, all single bonds, it's a tetrahedral shape because there's 4 bonds to every carbon. Okay, there's 4 groups attached to carbon. So it's a tetrahedral shape and it's 109.5 degrees around every bond, and these rotate freely in space. Nothing locks them in place. Okay, let's go to ethene with our double bond. The double bond, now we have 3 groups attached to this carbon atom. So 3 groups spread apart as far as I can is going to be 120 degrees apart because a circle is 360 degrees and a third of that is 120. So every one of those 3 angles is 120 degrees to make 360. Okay, so we have 120 degrees if it's a double bond, and this locks it in place. You can see now we have a locked bond. Okay, so we can have the possibility of cis-trans isomers that we talked about. Okay, with ethine, with the triple bond, the bond angles are 180 degrees. There to there is 180 degrees. There's 2 things attached to it. The farthest apart you can get in 2 with both negative charges is 180 degrees apart. So if it's all single bonds, it's a tetrahedral shape of 109.5 degrees. Okay, if it's a double bond, okay, you've got 3 attaching groups, each one's 120 degrees. Okay, it's a what am I trying to think of? Trigonal planar is the terminology I was trying to think of. Okay, so this is trigonal planar. And this is tetrahedral. Those are shapes we studied when we did the VSEPR in Chem 3. So this tetrahedral, trigonal planar, and this one is linear. Those are the 3 shapes you get depending on if it's a single bond, double bond, or triple bond. The double bond is 120 degrees, all in one plane. The triple bond is 180 degrees. That's obviously also one plane, it's a line. Okay, so there's our angles. So in the basic tetrahedral shape of all saturated, okay, if it's a saturated hydrocarbon, everything's at 109.5 degrees, and it's just a zigzag shape, one up, one down, one up, one down. Remember the configuration we had that are most stable? Okay, rather than bending back up and getting in each other's way, these just spread out in a zigzag pattern. Okay, you get a planar configuration around the double bond that locks it in space. Then the rest go back to zigzag pattern. Okay, that's your double bond, and it's 120 degrees, and it's trigonal planar. Okay, the other configuration would be linear with a triple bond. Then it goes back to the zigzag pattern after that. Okay, so what you need to know is the linear ones are 180 degrees. That's your triple bonds. The trigonal planar ones are 120 degrees. That's your double bonds. And the single bonds are your tetrahedral shape, which is 109.5 degrees. Okay. Different physical properties, okay, of alkenes and alkynes. Okay. Alkenes and alkynes are nonpolar. They do not dissolve in water. Okay. There's no hydrogen bonding with them. There's no polar mol ends it. So they're nonpolar. So they're not soluble in water. They are soluble in nonpolar solvents. Remember, the rule is like dissolves like. If it's polar, it dissolves in polar media. If it's nonpolar, it'll dissolve in a nonpolar media. And if you look at the physical properties, look at the molecular formula, And you can look at the melting points and boiling points. Okay. As the number of carbons increase, okay, the melting point and the boiling points also increase. The bigger it is, the more carbons there to hold together, the higher it's going to be to separate those intermolecular forces apart. So your melting point increases and your boiling point increases as the number of carbons increase, as they get bigger. Oops. Okay. So base names from the longest carbon chain. Remember, longest continuous carbon chain. We're still going to do that. And we have to be containing the multiple bond. So now we got another rule. We have to have the chain that we're counting contain the double or triple bond. Okay. Even if it's not the longest possible chain, it's the one that goes through the multiple bond. And we're going to change our ending. Instead of A and E, if it's a double bond, it goes to E and E. If it's a triple bond, it goes to Y and E. That tells us what type of bond it is. We're going to number from the end that will give the first carbon of the multiple bond the lowest number. Okay, so when we have multiple bonds, now the substituents are second rated. The multiple bond takes precedence. So we're going to give the multiple bond the lowest possible number, then the substituents. Okay, you prefix a name with the number of the first multiple carbon bond. Okay, and the prefix branch and substituents names, same as you did for alkanes. Okay, we'll give some examples as we go along here. So everybody remember how to name that one, CH3-CH3. What's that name?
Ethane.
Ethane, perfect. 2 carbons, A and E ending. Okay. If you have 2 carbons in a double bond, that would be
Ethene.
ethene, E and E. And if you had triple bond, it would be
Ethine.
Fine.
ethine, perfect. Okay. Now we don't put numbers on these because there's only one place it can be, but we can put them up at a different location. Then we got to say where it is, like 1 propine or 2 butine or butene. We got to tell you where the multiple bond is. But on these, it doesn't matter. It's only the number 1 carbon. It's only 2 carbons on it. Okay. CH3, CH2, CH3. What's that name?
Propane.
Propane, right? A and E ending. All single bonds. Propane means 3. Okay. There's a bond there. What would that be?
Propene.
Propene. Perfect. And again, if it was over here, this one on this side, it would still be the same because we just count right to left. So it's still propene. So you don't have to put a number on it. And this one here would be
Propine.
Fine.
pine. Perfect. Got it. All right. Now, we're going to make the longest carbon chain that includes the multiple bond. So how many carbons?
7.
Oops, I didn't want to do that yet. Wait, it went back to everywhere here. When the computer goes back, it really goes back. There's 7 carbons on that compound. Get back to it before I put the name up. Okay. So here's our longest chain. Everybody agree?
Yes.
Okay. We're going to count to give the multiple bond the lowest number. So did I start from right to left or left to right?
Right to left.
Right to left, because this gives you 1, 2, 3, 4, 5, 6, 7. Okay. If I did it the other way, it'd be 1, 2, 3. The beginning of the middle bond will be at number 4. So this way, the lowest bond has the lowest number. Okay. So we had put our parts together. We have substituent groups. Okay. We have 1 here. We have 1 here that's hanging off there. So we need to number those. Okay. So at number 6, we have, what's that? What's a 1 carbon group?
Methyl.
6 methyl. And we have at number 3, we have what kind of group? An ethyl group. Okay. So naming this thing, we have, and again, it's alphabetical order. So we would put 3 ethyl, 6 methyl. Now we got to say where the double bond is. Because we don't know where it is, we don't tell them. It's at the number 3 position. That's the first one. So it's 3 and 7 is heptene. By putting all those together. That's how we do it. Oh man. This keeps jumping backwards. I catch back up again. Okay, there's our compound. And that's what we put together. So 3 ethyl, 6 methyl, 3 heptene. Okay, this tells us there's an ethyl group at the number 3 carbon. There's a methyl group at the number 6 carbon. We have 7 carbons in our chain. And at the third one, there's a double bond. That's what it says. So it tells you exactly what kind of compounds you have. All right. Second one. Okay. What's the longest carbon chain? How many carbons? 6. Perfect. So there's your longest chain. And you have 1 substituent group. Okay. Now, are we going to go left to right or right to left? Or does it matter?
It doesn't matter.
It does matter. Either way we go, the carbon of the multiple bonds could be number 3. But once the double bond is, then we go by substituents. So if it's the same for the double bond or multiple bond, then we go by the substituent. So which way gives the substituent the lowest number?
Left to right.
Left to right. Okay. So you would assume it wouldn't matter because both are number 3 for the multiple bond. But you have a substituent there also. So if there's a tie with the double bond or the triple bond, then you go to the substituents. You go down to the next layer. So the multiple bond comes first, then the substituents come into play. So we're going to go left to right. So it's going to be 1, 2, 3, 4, 5, 6. So at number 2, we have what?
2 bromo.
Yeah. Number 2, we have 2 bromo. And then the multiple bonds at number 3. So when we put this together, we're going to have a 2 bromo. And then we're going to have 3. It's going to be a multiple bond. And it's 6 carbons, so it's hex. And it's a triple bond, so it's YNE. So put all that together. And we have 2 bromo, 3 hexine. Tells you number 2 position, there's a bromine. You have 6 carbon chain, that's your hex. And there's a triple bond because of the YNE. And look where it is. It tells you that's at the number 3 carbon. So the triple bond begins at number 3. So 2 bromo, 3 hexine. And this one, how many carbons?
4.
4 carbons. And are we going to go left to right or right to left now?
Right to left.
Right to left. Because it doesn't matter in the double bond which way you go. But now we go to the substituent groups. We have a chlorine over there. So we're going to go 1, 2, 3, 4. So at number 2, we have a substituent group. And then at number 2, we have a double bond. So it's going to be 2 chloro, 2, and we have 4 carbons, so bute, and then E and E is our double bond. So you'd have 2 chloro, 2 butene. Okay. So our number 2 position, we have a chlorine. We have 4 carbons. There's our bute. we have an E and E, which is a double bond at number 2. Okay. Triple bond this one. How many carbons in the longest carbon chain?
6.
So it's going to be a hex. And it's going to be a YNE because of triple bond. Are we going to label it from left to right or right to left? Which are we going to count?
Left to right.
Left to right, because it give the substituent the lowest possible number. Because a triple bond makes no difference which way we go. It's a tie either way. It's number 3. So then we go down to the substituent to determine it. Okay. So we've got number 2 bromo. And we have got number 3 hexyne. So 2 bromo, 3 hexyne. Again, it tells you at the number 2 position, we have a bromine. We have a 6 carbon chain, which is your HEX, with a triple bond, that's your Y and E. And it tells you it starts at the number 3 carbon. There's an interesting one. All right, longest carbon chain we look at. And remember, the carbon chain has to include the multiple bond. Okay, so what's our longest carbon chain? How many carbons?
8.
So 8. So it's oct. And there's a double bond, so it's E and E. Now, are we going to count left to right or right to left? Or does it matter?
Left to right.
Left to right.
Because
Left
the
to right.
double bond is closer to that side.
Perfect, because it's exactly right. Because the double bond's closer to that side. The double bond is in the third one to go left to right, and it's in the 1, 2, 3, 4, 5th one if we go right to left. So we're definitely counting left to right. So number 1, number 2, number 3, 4, 5, 6, 7, 8. Okay, so it's octene, and it's going to be 3 octene because that's where the double bond is. And we have attachments at 2 and at 6. So we have 2, 6, and then what? How do we say that? The attachments.
Dimethyl.
Dimethyl. There's 2 methyl groups, so dimethyl, 3 octene. So we have 2, 6 dimethyl, 3 octene. Would be the answer. 2, 6 dimethyl, 3 octene. Again, if you just look at it logically, it tells you at number 2 and number 6 carbons, you have 2 methyl groups. We have an octenes, you have 8 carbons. At the third one, we have a double bond. It's actually a pretty logical system. All right, next one here. This is our longest carbon chain. Excuse me, includes a multiple bond. Okay. Are we going to label left to right or right to left? It doesn't matter.
Doesn't matter.
Doesn't matter. I mean, I realize it can be different when we do it, but we have a substituent group that's going to be, either one's going to be the same. So you can go left to right, right to left, either one would be acceptable. Okay. So 1, 2, 3, 4, 5, 6. So we've got 6 carbons, which is hex, double bond number 3. And we got an attachment here, which is chloral. We got an attachment here, which is methyl. Okay, so it's going to be 3. If you have all this together, we have 3 chloral. And we have a number 4 methyl. And you have a number 3. And this is hex. And it's a double bond, so hexene. Those are all our parts. Then you put them together. Okay. So we've got 3 chloral, 4 methyl, 3 hexene. Okay. Or 3 chloral, 3 chloral, 4 methyl, 3 hexene, just like we said. Okay, making sense? Perfect. Good.
Yes.
All right. All right, now I've got more than one double bond. We couldn't keep it easy, right? Got to give you guys a challenge sometime. Alkenes having more than one double bond, which a lot of compounds do. It's an alkyl. If it has two double bonds, it's the alkyl-diene. Remember, di means two. If there's three double bonds, it's going to be triene. If there's four double bonds, it's going to be tetraene. All depends on how many double bonds you have. So 3 bonds is triene. Same for alkynes. If it's 2 bonds, it's a dial. It's a diene, Y-N-E, or 3 bonds, it's a tri-Y-N-E. So this would be your alkane, ALK, whatever it is there, alka, and then this would be diene for triple bond, or triene for 3 triple bonds. Okay, and you give the numbers of where they're located at. Okay, so here we have a compound. Longest carbon chain is very simple. There's only one chain. Are we going to number left to right or right to left?
It doesn't matter.
Doesn't matter. If I go left to right, my numbers are 2 and 4. If I go right to left, it's 2 and 4. Makes no difference. So just might as well have put them over there. Might as well go this way. 5, 6. Okay. So this is a what is 6 carbons?
I didn't hear what you said. It cut out.
Oh, that's it. What's the root for 6 carbons?
Hex.
Hex. Perfect. Okay, so we're going to have hexadiene because there's 2 double bonds. Okay, so it tells me my hexa is my root, 6 carbons. I have 2 double bonds E and E, and they're at 2 and 4. So 2, 4 hexadiene. Okay, remember there's a comma between numbers. There's a dash between numbers and letters. And it tells you hexa, so you write 6 carbons, and then 2 double bonds, diene. One's at 2, one's at 4. Okay, again, another compound. Doesn't matter if it's how many carbons. There's our chain. 1, 2, 3, 4, 5 carbons. Okay, left to right or right to left.
Doesn't matter.
Makes no difference. We're gonna have one at 1, 2, 3, 4, and 5. So it's going to be, the ending's going to be E and E because it's double bonds, and there's 2 of them. So it's going to be a diene. 5 is penta. So you're going to have a double bond at number 1 and number 4, pentadiene. So 1, 4, pentadiene. Okay, tells you where your double bonds are at. 5 carbons, 2 double bonds, E and E is your double bonds. All right, how many carbons in the longest chain?
9.
9. So it's going to be nona. 9 is nona. Okay. Left
I
to right
really
or right?
thought way too hard. I thought it was like a trick question because it's just a straight line, so I just didn't.
No, no trick question. It's just a straight line. It's 9 carbons. Don't overthink things. If there's a simple answer, usually that's the right answer.
From my mom, so
Yep. She did the same thing. Yep. So nona. Okay. Left to right or right to left?
Left to right.
Left to right. That's going to be the lowest number to the multiple bonds. So this one's at number 2. 3, 4, 5. 2, 3, 4. And this is at number 5. So we got 2, 5. Right? Nona. How many double bonds we have? We have 2. So diene. 2, 4. Nona. 2, 5. I'm sorry. 2, 5. Nona. Diene. Okay, and name tells you exactly what it is. You see that E and E, you know it's a double bond. You see the di, you know there's two double bonds. You see nona, you mean the whole compound has the longest carbon chain, has a 9 in a row, and then the 2 and the 5 are where two double bonds are located. Okay. Again, let's see. How many carbons? No trick question on this one.
7.
7 carbons. Okay. Left to right, right to left.
Left to right.
Left to right.
That's right. So 1, 2, 3, 4. Okay. So it's going to be a diene ending because you have 2 double bonds and they're 2 and 4. And there's 7 total. So 7 is hepta. So put all together, you've got 2, 4, heptadiene. Double bond, 2 of them, 7 carbon chain. At 2 and 4 are your double bonds. All right. Now it's a trick question. It's not easy to count that one. Okay. I mean, it's not a trick question, but you got to think now. Okay. The carbon chain is going to be a cycle, right? It's a circle. You have to give the lowest number to the double bond, and it has to go through the double bond. I mean, you can't start here and go 1, 2. You have to go through the double bond first. So you'd have to start either here or here to count, or here and go this way. Which way, as we travel around here, is going to give the double bonds the lowest possible number, and the substituent the lowest number also with it, if it's a tie. So which way are you going to number this thing?
Bottom left.
Bottom left. So that'd be 1, right? Okay, you got to go through the double bond. That would be 2, 3, 4, 5, 6. That gives you double bonds at 1 and 4. And it gives you substituent at 3. Okay. If I would have gone started right here and gone this way, they still would have given me double bonds at 1 and 4, but the substituent would now be at number 6 instead of 3. So we went the right way, so that's perfect. Okay, everybody see why? You got to give your double bond, your multiple bond, the lowest possible numbers you can. And then once those, when that's determined, then you got to give your substituent the lowest number after that. Okay, so this would be a cyclo what?
Hexene.
Hexene, perfect. Okay, but there's 2 double bonds. So it'd be a cyclo, hexa, and how many double bonds do we have? Hexadiene. Okay, but it's a hexene, you're right. So 6 carbons, double bonds, but there's 2, so you got to put the di in there. So it's a hexadiene, and it's a cyclo. Okay, and the double bonds are located at 1 and 4. So 1, 4 cyclohexadiene. Is that right?
Yes.
Someone say no. Tell me why. What are we forgetting?
Substitute.
The methane.
The methane. Perfect. So it's 3 methyl, 1, 4 cyclohexadiene. That makes it correct, because then we don't forget the methyl group. So if you remember, I told you do organic chemistry always backwards. So you have a cyclo hexa, 6 carbons in a circle. 2 of those are going to have a double bond at the numbers 1 and 4 position. And on top of that, after that, we're going to have a methyl group at number 3. So the correct name for this on your exam is going to be, that's a hint, on your exam would be 3 methyl, 1, 4 cyclohexadiene. Take your time with these. They're not as intuitive as the straight chain ones. Like Donovan said, they're not meant to be tricky, but if you look up and all of a sudden you got all these things coming off, just take a step back and think about it. and you'll be able to think it right through. Okay. So to review that, okay, we give our double bonds the lowest possible number. Now this one, double bond is going to be the same whether they go left to right or right to left. But are we going to go left to right or right to left?
Left to right because the constituent is closer to that side.
Perfect, because the constituent methyl group is closer to the left side. So it'll be 1, 2, 3, 4. And it's going to be, 4 is butyl. So it's going to be butyl or butadiene. Everything will be at 1 and 3. That's where double bonds are located. And number 2 is going to be a methyl group. Okay. So the longest longest chain containing the double bond is butane. Okay. There's positions that double bond at 1 and 3. So it's 1,3-butadiene. Okay. There's a substituent group at number 2, which is a methyl group. Once you have that, you just put them together. 2-methyl, 1,3-butadiene. Commas between numbers, dashes between numbers and letters. So it'll be 2-methyl, 1,3-butadiene. To exactly what the compound is. Okay. Now what do we got? You have to have the longest chain, including the multiple bond. So it's got to include the multiple bond. So you got to go here. This would be 1, 2, 3. This would be 1, 2, 3.
8.
So
Wouldn't it be 8 just going straight?
1, 2, 3, 4, 5, 6, 7, 8, or okay. So why couldn't you go this way? 1, 2, 3, 4, 5, 6, 7, 8.
Because going from right to left gives a double bond a smaller number. Or
No,
yeah.
you have to include double bond in your longest chain. If I went this way here like this and got 8, that wouldn't include the double bond.
Oh, I thought you were just talking about counting from left to right.
Well, yeah, so it would count the other way too. But you got to make sure your double bond is in the longest chain. And you're right, you got to count from right to left to give the double bond the lowest possible number. Okay, so your longest chain has to have the multiple bond in it. And then you have to give it the lowest possible number. So this would be 1, 2, 3, 4, 5, 6, 7, 8. All right. So 8 carbons is what?
Octane.
Okay, octane is 3 carbons, and then it's going to be octene because there's a double bond. There's only one, and it's number 3, right? At the number 3 position. So it's going to be 3 octene, and we got substituent groups hanging off it to name. We got one here. We got one here. So our substituent, our first one is at number 3. What is it? It's going to be 3 methyl, and then at number 4. I can't read my own writing. And number 4, there's going to be a
Propyl.
propyl group. Perfect. Okay. So you're going to put everything together at alphabetical order: 3 methyl, 4 propyl, 3 octene. Putting it all together. Longest chain containing double bond is octane. It's a double bond at number 3, so it's 3 octene. Substituent against our 3 methyl and 4 propyl. Putting all that together, we have got 3 methyl, 4 propyl, 3 octene. If you look at the name, it tells you everything about the compound that you need. Okay, it tells you there's an octene group, which means 8 with a double bond at number 3. Okay, there's a methyl group at number 3 and a propyl group at number 4. Oops, wrong button. Okay. Longest carbon chain again, including the multiple bond. How many carbons?
6.
Okay, so 6 carbons. And 6 means what?
X.
X.
Okay, it'd be hexane, it's 6 carbons. And then instead of Ane, we have a triple bond here. So what's our ending going to be?
Hexine.
Hexine, perfect. And are we going to number right to left or left to right?
Right to left.
Right to left. 1, 2, 3, 4, 5, 6. Okay. It's 3 for the triple bond no matter which way, but the substituents are lowest if we go through the right from the right side. So we got hexine and we got the triple bond at number 3. Okay. And at number 2, we have what?
Methyl.
Methyl, how many?
2.
2. So at number,
Dimethyl.
okay, it's 2
Two,
Two.
dimethyl.
dimethyl. Perfect. So you got 2,2-dimethyl, 3 hexine. Longest carbon chain was hexane. It's a triple bond, so it's a YNE ending right here, and it's at the number 3 position, 3 hexine. We have 2,2-dimethyl as our substituents. Put it together. 2,2-dimethyl, 3 hexine. Okay, so if you look at the name, it tells you everything you need to know about the compound. So now we can do single bonds, we can do double bonds, we can do substituents, we can do cyclobes. Okay, we're getting close to having everything we need to be able to do all the rest of the stuff now. So now each of these are according to the IUPAC names. All right, take a look at that. Find our longest carbon chain, always go through that. Just do this and then put our numbers. Are we gonna go left to right or right to left?
Left to right.
Left
Left
to
to right. Even though the substituents would be lowest if it went to the right, the double bond, in case of multiple bond, would be lowest if I went left to right. And there's 7. Okay, so how do we put this together? What do we call the root, the long chain? What do we call it?
heptene.
Heptene, right? What's the number you're associated with it?
2.
Okay, so 2 heptene, perfect. Okay, that's our chain. Now, what are the substituents grouped?
4 methyl and
Is it-
6 chloro.
4 methyl and 6 chloro. Alphabetical order would be this chloro comes before the methyl and put them together. So we would have 6 chloral, 2 methyl, 2 heptene. Just like that. You are going to be experts at these. 6 chloral, 4 methyl, 2 heptene. Okay, there's another one. Okay, what's our root chain, longest chain?
Pentine.
Okay, okay. So it's pentane, and then it's triple bond, so it's Y and E. Is that right?
Yeah. No?
No, why not? Someone say what's wrong with that?
Because there's 2.
Perfect, there's 2 of them.
Okay.
So what would it be?
1, 4.
Not yet. But what was
Dipentine.
pen,
Diene.
Oh, okay.
Oh, pentadiene.
diene, 2 double bonds. So pentadiene. Now you're 1, 4. Okay. So the root chain is 1, 4, pentadiene. And no substituents attached, right? Remember, you got to name how many double bonds or triple bonds that you have. So it's a triple bond at 1 and at 4. It's 5 carbons long, and there's 2 triple bonds in the compound. Okay, perfect. All right, 1 triple bond. You have the longest chain. And are we going left to right or right to left?
Left to right.
Left to right. Okay, so what's our root name?
Heptine.
heptine. Because there's 7 carbons, right? So it's heptine, just like you said, perfect, only 1 triple bond. And what's the number we associate with that?
3.
3. So it's 3 heptine. And we have a substituent. What number is that at?
5.
So it's 5, and it's bromine, so it's bromo. So put it together. 5 bromo, 3 heptine. Okay. Triple bond, 7 carbons. The triple bond's at number 3 carbon. There's a bromine at number 5. That's how we check everything. Okay. Longest chain is the chain going straight across.
7.
1, 2, 3, 4, 5, 6, 7 carbons. So it's hep. Okay. And left to right or right to left?
Right to left.
Right to left. So we got 1, 2, 3, 4, 5, 6, 7. Okay. So how many double bonds do we have?
2.
2. So it's heptadi, and then double bonds are E and E. And they're what numbers?
1,
And
5.
5. Perfect. 1, 5 heptadiene. So naming cycloalkanes. Again, cycloalkanes are alkanes that are in a circle. Cycloalkanes are named just like, cycloalkenes. I said cycloalkanes. They're named just like cycloalkanes, except we put an E ending on that, and we tell them where the double bond is located. All right. So we prefix a name with cyclo, which means it's a continuous circle. Okay. Numbering must start at one end of the double bond and pass through the double bond. Like I said, you can't start it at the end of the double bond. It has to pass through. So when if you put number 1, number 2 has to go through the double bond, and then you put number 2. Okay. Substituents must have the lowest number after give the lowest number to the multiple bonds in the cyclic compound. Okay. Either numbered clockwise or counterclockwise to give the lowest number possible. Just like we did with the alkanes and alkenes that were linear. Okay, we number left to right or right to left. If they're cyclical, we either light them clockwise or counterclockwise. Same logic. Okay, look at that compound. All right, so now we've got, let's do the base name. It would be a cyclo what? Cyclohexene,
Hexene.
because there's a double bond. Now we got to put the double bond at number 1. Which one's going to get is it the
Very
bottom here or the side here? We put number 1. Was
The
that
bottom to the right.
okay? Bottom one to the right, and then we're going to go clockwise or counterclockwise.
Counterclockwise.
Counterclockwise goes this way. It gives this number 2, and gives this number 3, 4, 5, 6. Okay. If we would have done it the other way, if we would have put the number here, this would have been number 1, 2, 3. The substituent had number 4, but this way the substituent has number 3, which is a lot low, which is lower. So this is the correct way to do it. You give the double bond the lowest number, and you put it whether it's clockwise or counterclockwise, depending, and it has to go through the multiple bond. Okay, and then we give the substituents the lowest number possible, and then we have the numbers assigned. So this is cyclohexene. Right. So at number 3 we have what?
Methyl.
Methyl.
3 we have methyl, and 5 we have
Chloral.
chloral. So it's 3 methyl, 5 chloral, 1 hexene. You can leave the one on or leave the one off. It doesn't matter because you're putting the number one at the lowest position. So the double bond has to be number one. So sometimes you'll see the number one would not, but if the number one's not there, we know it's number one. Okay. Everybody get that? Because you're going to make your double bond the lowest possible number, which is number one. So you have to put a one on the double bond. Everything else gets determined. Okay. So if you don't see that any number there, it's number one. We know when it has to be number one. So it's 5-chloro, 3-methyl, chlorohexene. It would not be wrong to put 5-chloro, 3-methyl, 1-cyclohexene. Okay, that would still be acceptable. Okay, that makes sense, everybody?
Yes.
Okay, perfect. Okay, so that's how we name cyclohexenes. All right, let's start again. We have to get the double bond the lowest number. So I put the one on the top or to the left? In other words, do I put the number one here or here? Because one of those has to get it.
The one on the left.
Okay, put the number one right here. Okay. And then we have to go through the double bond. So that becomes 2, 3, 4, 5, 6. Okay. The other way, if I did number one on the top, it'd be 1, 2, 3, 4, 5 would be the substituent. So this is the correct way. So again, this is a cyclohexene, same as before. And at number 4, there's a chlorine. So what would the name be? Who wants to try guess at the name?
4-chlorocyclohexene.
Perfect. You got it. Exactly right. Parent chain is a cyclohexene. Position the double bonds has to be 1 and 2. Substituent is 4-chloro. You put them together. 4-chlorocyclohexene. Again, you can put 4-chloro-1-cyclohexene, but it's kind of redundant because we have to give it the lowest number, which is number 1. So 4-chlorocyclohexene. Okay. So this is a cyclo what?
Pentene.
Pentene. So this is your cyclopentene. And do I give this one the number 1 or this one the number 1? A or B?
A.
A.
A. Perfect. Because that's going to give this the lowest number. 1, 2, 3, 4, 5. So we have a methyl group at number 3. That's it. We put them together. So what's the name?
3-methylcyclopentene.
Got it. Perfect. 3-methyl, because their parent chain is cyclopentene. We got the position double bond where one has to go through it. So it has to be a counterclockwise position. Substituent is 3-methyl. And the name put together is 3-methylcyclopentene. It tells you everything that you need right here, right? Okay, it tells you it's a pentene, it's 5 carbons. E and E is your double bond. Cyclo is a cyclical compound. And at number 3, there's a methyl group. That one's kind of neat. So we got to start the double bond, the lowest number. So this is going to be our A position. This would be our B position. So do you label it number, is the first, we label number 1 at the A or B position?
A.
So this becomes 1. Then what? It becomes 2. And that becomes 3, right? Everybody agree?
Yes.
Someone say no and tell me why.
Oh.
Oh. This is one of those when Donovan would say, oh, but straightforward. This is not straightforward.
Oh. Is it because the chloro and the beginning of the double bond is at the same part, same spot?
Bingo. If I number this 1, this 2, and this 3, now my substituent is number 1 rather than number 2.
Yes.
Number 1's lower. Very good. So that's the correct way to number it. Okay. This becomes your number 1 carbon because this way you have a 1 chloral rather than the 2 chloral. Okay. It's kind of tricky because you don't see that at first. Almost everybody misses that one. That's why I put the lower letter here so you'd miss it. Okay, because that's how you learn. Because this is the number 1 carbon, because that gives your chlorine the lowest attachment. So 1 chloral, and then you have this is a cyclo what?
Propene.
Cyclopropene. So you have 1 chloral cyclopropene. You have 1 chloral cyclopropene. Everybody understand why this is labeled number 1 now? Because this gives chlorine the lowest possible number. And you
Do we
have to,
put the 1 since they're both at the same, since they're both at 1.
what's that?
Do we have to put the 1 since they're both at 1?
You have to put the 1 for the chlorine. Because you could put the chlorine could have been here away from the double bond. But the double bond, you have to give the lowest number 2. But you still got to put the 1 chloral. Because you got to tell me where the chlorine is. Because it's somewhere different. But the double bond has to be the lowest number. The substituent is the second one that comes into effect. Remember, you have to name the double bond the lowest, and then you try after you do that to get your substituent the lowest number possible. But so you got to tell me where that one is. Does that make sense?
Yes.
Okay, so you do need the one here. You do need this one right here. You have to put 1 chloral, but you do not need the one for the double bond because that's going to be assigned number 1. But you got to tell me where that chlorine group is. All right. Okay, there's a double bond. We have positions A and we have position B. Where's number 1 going to go, A or B?
It doesn't matter.
Same on each side.
The same either way. If I put the
Yes.
1 there, it'd be 2, 3, 4. 1 there would be 2, 3, 4. Either way is fine. Perfect. Let's put this as 1, a 2, a 3, a 4, a 5, a 6. All right. So what's the root compound we have? Cyclo what?
Cyclohexene.
Excellent.
Cyclohexene. Cyclohex, that's an X, hexene. Okay. And we have what do we have? What are our substituents?
Hexene at 4 and 5.
So 4, 5,
Dimethyl.
dimethyl, right?
Mhm.
Okay.
And then is it cis?
Very good. It's cis. Notice both these, because once you have a cyclical compound or a multiple bond, it locks it in place. These are both going above the plane. So this would be cis cyclohexene. I'm sorry, cis 4,5-dimethyl cyclohexene. That'd be the complete name. Don't forget the cis. Okay. So it'd be cis 4,5-dimethyl cyclohexane. The cis refers to it being on same side. 4,5-di gives you 2 methyl groups at 4 and 5. And cyclo is your cyclical compound. Hex is your 6. E and E is your double bond. Okay, so it tells you everything about the name right there. And very good. Good catch on the cis. They're both going up. Okay. All right. So here's our double bond. This is A, this is B. Which one gets the number 1 count, A or B?
A.
A becomes number 1. Then it goes through the double bond, 2, 3, 4, 5. Okay, and these are both in what position? They're both going up, right?
Yes, so it's cis.
Cis. And this would be a cyclo. What's 5?
Pentene.
Pentene.
Pentene, perfect. And we have bromines at 3 and 4. So di bromo. Put it together. What's the name altogether?
Cis 3,4 dibromocyclopentene.
Perfect. Perfect.
Is there supposed to be oh, it's never mind, it's a dash. I thought it was a space between the cis.
No spaces. Okay, that no spaces. There are some exceptions, but for the most part, no spaces. Dash between letters and numbers, commas between numbers.
Okay.
So cis 3,4 dibromo cyclopentene. All right. So do we start counting at A or B?
A.
Start counting at A. Everybody see that? If we started counting at B, it would go counterclockwise because you have to go through the double bond. So 1, 2, I don't need that line there. 3, 4. All right. So is this cis or trans?
Neither.
Very good. It's neither. There's no such thing. There's only one substituent. You got to have 2 substituents. You have something that locks it into a plane. Okay, so you can't have cis or trans in this compound. So this is a cyclo what?
Butene.
Butene, perfect. 4 carbons, double bond. And this is a fluoro at number 3. So put this name together. What do you got?
3-fluorocyclobutene.
Perfect. 3-fluorocyclobutene. Got it. Okay, draw a complete structural formula for each of the following. So now we get to draw them. Okay, drawing is very easy. Let's do this one, then we'll take a break and do the rest. So we always work which way in organic chemistry?
Backwards to front.
Backwards. Perfect. Work backwards. So hexyne means what? How many carbons?
6.
6. Hex means 6. 1, 2, 3, 4, 5. Just draw 6 carbons. Easiest thing to do. And number 3, what does that Y and E tell us?
Triple bond.
Triple bond at the third one. There's a triple bond. At number 1, there's what?
Bromine.
Bromine. Everything else is hydrogens. CH2, 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 CH3. Here's a dash here, a line. That's it. So if you make it neater, it would be bromine, CH2, CH2, C, triple bond, CH2, CH3. That's your structural formula. Okay. Draw the line formula. Again, if you want to draw the line formula, same way. There'll be 6 carbons. 1, 2, 3, 4, 5, 6 carbons. At the third one, you make a triple bond. At the first one, you make a bromine. There's your line structure. That's what there is to it. And that kind of made a mess through what I had to draw, huh? Let me do it so I can get some rid of, probably not gonna go back far enough to get rid of these. Wonder if I can just erase some of these. Oh, it's erasing some, getting out of your way. Here we go. Just guess you can see it. Perfect. Okay, we'll do the line structure. I guess we will do line structures. So there are 6, 1, 2, 3, 4, 5, 6. The third one was a triple bond. First one was a bromine. That's it. So there's your line structure. There's your structural formula. So 2-butyne. How many carbons?
4.
4. Perfect. Butyne is 4 carbons. So let's put it. I'll try to get so I can get in the way of the next one I'm going to do. So 4 carbons. Okay. And this tells you at number 2 there is a triple bond. That's it. So 2-butyne would be CH3. So the second carbon, there's your triple bond. That's 2-butyne. To do that on a line formula, you draw four carbons, 1, 2, 3, 4. And the second one, make a triple bond. That's 2-butyne. Both structural formula and line formula. Okay. Dichloroethine. Okay. How many carbons?
2.
2 carbons. That's it. And then the Y-N-E ending means they're a triple bond. And dichloro means there is 2 chlorines. You do not need numbers because that's the only place you can put them, right? There's no other spots available. Okay. Line formula would be 2 carbons, triple bond, chlorine, chlorine. Would be your line formula. But that's dichloroethine. 9-iodo-1, no 9. So you got NON means 9 carbons. At number 1, there's a triple bond. At number 9, there's an iodine. So you make 9 carbons. At number 1, you put your triple bond. At number 9, you put your iodine substituent. Okay. So line formula would be 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Triple bond at number 1. Iodine at number 9. That's the line formula. All right, now we're going to name. Okay, you've got nomenclature. How many carbons? 5 carbons. Okay, we're going to go left to right, give the multiple bond the lowest number. Okay. So this is 5 carbon is pentane, and it's going to be pentyne because of the triple bond, and that's at number 2. And there's no other substituents. So 2-pentyne. Okay. Same thing here. We're going to number from right to left to give the multiple bond the lowest possible number. So 1, 2, 3, 4, 5, 6, 7. So our root one is heptane. It's going to be heptyne. 7 carbons, triple bond, and that's at number 1. 1 heptyne, and then 2 attachments. 4,5-dibromo. So 4,5-dibromo, heptyne. Again, you don't need number 1 because if it's at the number position, we just assume it's number 1. It's not there. Okay. Nice. Huh? Sorry. All right. Look at this one. Longest carbon chain is right there, which includes the multiple bond. Are we going to go left to right or right to left?
I don't think it matters.
Doesn't matter. Be the same either way. So we'll put 1, 2, 3, 4, 5, 6. Okay. We got substituents here.
Only time that it won't.
What's that?
And is the only instance where it won't matter left to right is if it's identical in either direction.
Correct. Identical either direction, but it makes no difference then, yes. Same way, either way you number. And a substituent here. So we have got 6 carbons. So 6 carbons is hex. And it's a double bond, so it's hexene. And the number for that double bond is 3. So 3 hexene is the main chain. Substituents. We've got 3 methyl groups. So where are the methyl groups at?
2, 4, and 5.
2, 4, 5, tri methyl. Yeah, sure. Go ahead. Get through back there. All right. You going through pumps? Dogs through the... No? Oh, he wanted to go see you. All right, so 2, 4, 5 trimethyl, and we have a chlorine group at number 3. So what would all that be put together? Do I have any takers? Huh?
2 chloro, 2, 4, 5 trimethyl, 3 hexane.
Perfect. 3 chloro. Oh, perfect. 3 chloro. So number 3 carbon there. 2, 4, 5 trimethyl, 3 hexene. Exactly what you put. Okay. Now, longest carbon chain. Okay. There's your longest carbon chain, which includes the multiple bond. That makes this a substituent and this a substituent. Okay. Are we going to number from left to right or right to left? Or top to bottom or bottom to top? Either way you want to do it.
Right to left.
Right to left. This is going to be 1, 2, 3, 4, 5, 6, 7. Okay. That's your longest continuous carbon chain that includes the multiple bond. So at number 3 is where our triple bond is. Okay. 7 is heptyne. Y-N-E, because it's a triple bond at number 3. Okay. Then we tell where our substituents are. At number 5, we have a methyl group. At number 2, we have a chloro group. Okay. So putting all together, alphabetical order, 2 chloral, 5 methyl, 3 heptyne. Okay. 2 chloral, 5-methyl, 3-heptine. Making sense? All right. Perfect.
Yeah.
Perfect. All right. Review all this, then we'll get into reactions. Let me eat here a little bit. Okay, when naming haloalkanes, double or triple bonds take precedence over a halogen or an alkyl group. In other words, you give the multiple bond the lowest number and then consider the substituents attached, just like we've been doing. Okay, so this is our substituent. Okay, and this is our group. We're going to assign this double bond to have the lowest number possible, and then go to the halogen. Okay, so are we going to go left to right or right to left?
Right to left.
Right to left, because that's going to give you your, it doesn't matter on double bond either way, it's still going to be a number 2. But this one here will get considered after that. So this will give this one the lowest possible number. So 1, 2, 3, 4. So it's 2 chloral, 2 butene is the number. All right, chloral group's at number 2. E and E is a double bond, 4 carbons at double bonds at number 2 position. If 2 or more halogens indicate the position of each one, just like we did. If it was 2, 3, we put that down there, dichloral. Okay, let's look at this thing. We going right to left or left to right?
Left to right.
Left to right. That'll give the triple bond makes no difference. Either way you go, but the bromine's going to be a lower number if I start from the left side. So 1, 2, 3, 4, 5, 6. All right. So 6 carbons is hex, and it's Y-N-E because it's a triple bond, and that's going to be at the number 3 position, and a bromine is going to be at number 2 as our substituent. So putting that together, we get 2 bromo, 3 hexine. Good. All right, again, longest carbon chain. Are we going to go left to right or right to left?
Left to right.
Perfect. This is going to be left to right because it doesn't matter about the substituent groups. What matters is it's going to give the double bond the lowest number because it's be different no matter where we go, which direction we go to be different. 1, 2, 3, 4, 5, 6, 7, 8. So a parent chain is what's 8 carbons?
Octene.
Okay, octene, double bond, and it's at number 3. That's your double bond starts right here at number 3. And you have 2 attachments, one at 2, one at 6. 6 di, because there's 2 of them, methyl. That's it. So you put that together, what will we have? We'd have 2,6.
2,6-dimethyl 3-octene.
You got it. Perfect. And everything's right in the name there. We know there's 8 carbons. We know there's 1 double bond at number 3. We know there's 2 methyl groups, 1 at 2, 1 at 6. It's all right in the name right there. All right. Left to right, right to left.
Doesn't matter.
Doesn't matter. I go 1, 2, 3, 4, 5, 6. Okay, so you have 6 carbons. One a double bond number 3, so you have 3 and 6 carbons is hexene, a chlorine at number 3 and a methyl number 4. So you name your substituents. You have 3 chloral, 4 methyl, 3 hexene. 3 chloral, 4 methyl, 3 hexene. That's how you name it. All right. If you thought it was too easy, here's another one for you. 8, 10, 12, triene. Okay. Now, I don't expect you to be able to name this yet, but you will be able to. What this tells you is that there's 3 double bonds, triene. One at the 8 position, one at 10, one at 12. Diene, there's 2 triple bonds, one at 4, one at 6. Heptadeca, there's 7, hepta 7, deca's 10, so 17 carbons. Diol, OL is an alcohol. We haven't done those yet, but those are these OH groups. Those are alcohol groups. And we'll do that next chapter. And there's 1 at 14, there's 2 of those. So any name you get, no matter how long it is, you can break it down and you can tell me what it is. Okay? You would have figured out everything out.
Can you point out the
This
third
is-
double bond?
Was that
Can you point out the third double bond?
the third double bond?
Yeah,
There's 1, there's 2, there's 3.
I'm sorry, triple bond. Sorry, the triple bond. I just see the 2 on the long line.
Right, here's a triple bond. Here's a triple bond.
Okay,
Yeah, di is only
okay,
2
sorry.
triple bonds.
I flipped them.
Okay. Yeah, there's 3 double bonds, 2 triple bonds. Okay. And this is cicutoxin. Cicutoxin is a very, very lethal toxin here in North America. Okay. It's one of the most lethal toxins that we have. Go sit down, Pompano. Right. It's a neurotoxin, which means it affects your nervous system. Produced by the water hemlock, okay, which is the same family of plants like parsley, celery, and carrots. It's our water hemlock. Cicutoxin is present in all parts of the plant, but is mostly concentrated in the root. Okay? So a single bite from the root has been reported to kill an adult. And this grows wild in the United States, in Northern America. Okay, so don't bite the roots. The roots are extremely toxic. The rest will make you sick. Eating a small portion, as small as 2 to 3 centimeters, can be fatal to adults. Okay, let me get my computer set. Cicutoxin acts directly on the nervous system. For those who have had anatomy with me, you know what this is talking about. Its signs and symptoms of cicutoxin poisoning include dilation of the pupils, affect the nerve, the muscle twitching, rapid pulse and breathing, violent convulsions, coma, and death. And it's rapid. Onset of symptoms is very rapid, and death can occur within 2 to 3 hours. There is no antidote. Nothing is going to cure this. Okay. The only thing you do for patients with cicutoxin poisoning is you support the functions. Okay. Only treatment, you're controlling the convulsions and seizures, preserve normal heart and lung function as long as you can, and hopefully gets out of the system and they recover on their own. But you cannot give them any medication that's going to help with this. There is no toxin. There's no antidote to it. Okay. Fortunately, cicutoxin is a very rare occurrence. Occasionally, animals will graze on the plant in the spring, results in the death of those animals in about 15 minutes once they eat them. Humans do not usually come in contact with water hemlock. Most recent cases involved individuals going after wild ginseng. It looks the same as ginseng and other wild roots. They mistake the water hemlock for an edible plant and they eat that. So if you're going after roots for ginseng and other health benefits, be really careful you know what you're getting. Okay, because cicutoxin, the water hemlock is not a nice one to get a hold of. Okay, it causes death by disruption of the central nervous system. Okay, it's a potential non-competitive gamma aminobutyric acid receptor antagonist. So it reacts against the receptors. In humans, citratoxin produces symptoms of nausea, emesis, abdominal pain within 60 minutes of when you eat it. Okay, can lead to tremors, seizures, and death. Historically, if anybody remembers their history books, citratoxin was used to kill who? Who in history was killed by citratoxin? Water hemlock, Socrates. Or have you ever watched Bill and Ted's Excellent Adventure? Socrates. No, Bill and Ted's Excellent Adventure fans, huh? Socrates was killed by suicide by drinking water hemlock. Okay. It's difficult, if not impossible, to detect during an autopsy. Usually, when someone dies of citratoxin poisoning, they determine that to be as natural causes. Okay, just because you don't like your spouse doesn't mean you got to go get some of this stuff. Okay, it's very hard to detect on autopsy because it works so fast. Okay, and that's what it looks like. This is water hemlock growing naturally. So if you see this stuff, do not confuse it with ginseng and some of the other edible plants that you use, and do not eat the roots of this.
So if you eat like the stalk of that,
You can get extremely sick. And if you're a small child, you will die from it. Adults usually will not die from just the stalk. They have to eat the root because of the body mass.
so when they like, how was Socrates killed? They were like, hey, you take some of this ginseng and he just
He put
bit
it-
into it.
He put in his tea. It's suicide. Socrates was suicide.
Oh, so he made a tea with the root.
Right. That's what he died of. And that's it close up. So if you see that plant, don't eat it. If you're going to eat ginseng and all that, make sure you know what you're getting. All right, more isomers. Because of unsaturation, a double bond. Yes, go down. Oh, that's good. All right. So carbon-carbon double bonds are rigid. They form a rigid structure. We do not have three-dimensional rotation around them anymore, like our single bonds. So therefore, if we have a double bond or if we have a ring structure, we've stabilized it in space. We've locked it in. So now we can have isomers are possible, whether they go above and below or above and below or both above or both below. Determines our type of isomers. Okay. So the orbital shape, which are those pi orbitals, those S and P and D and F orbitals we talked about before, those pi orbitals restrict the rotation around that double bond by locking the electrons in a specific pattern. Therefore, they can't rotate. Right? This gives you cis-trans isomers. It doesn't always give it to you. It makes it possible. It makes cis-trans isomers possible, depending on what else is attached. When you have a cis-trans isomer, you have to have two different groups on each of the carbons. Okay. You cannot have the same thing on one of the carbons. So it requires two different groups on each of the carbon atoms attached by the double bond. Okay. So 2-butene is the first example of an alkene, which can have two different structures based on restricted rotation about a double bond. Because it can have different things attached to it. So this is 2-butene. Here's your longest carbon chain, which is 4 carbons. And here's your longest carbon chain, which is 4 carbons. This double bond locks it in place. So you have got methyl groups up and down, hydrogens up and down. You got methyl groups on the same side, hydrogens on the same side. This is a trans isomer. This is a cis isomer. Cis means same side, trans means different side. Okay, so that would be trans 2-butene. Again, it's a trans relationship. There's 4 carbons with 1 double bond at the number 2 position. Okay. Look at the other one. One next to it would be
It's two
cis. Perfect. It's exactly right. It'd be cis 2-butene. Okay, butene, there's four carbons, double bond at number 2 position still, and the methyl groups are in a cis relationship to one another. Perfect. So identifying cis and trans isomers. If one end of the carbon-carbon double bond has 2 groups are the same, cis or trans isomers are not possible. So if one of the double bonds has 2 groups that are exactly the same, you cannot have isomers. You cannot have cis trans isomers because no matter how you rotate it, it's going to be the same. In other words, if you had CH3 bonded to this, bonded to CH3, and there's your double bond. Okay. If we replace this up and down, it'd still be the same. So if you have the same group attached, you cannot have cis or trans isomers. Not possible, even though you have a double bond. Both carbons of the carbon-carbon double bond must have 2 different groups attached. Okay. So both of them have to have different groups attached. If one has the same group attached, it is impossible to have a cis-trans isomer. It will not exist because it can't switch places. So you find a group common to both ends of the carbon-carbon double bond, and you compare them. Like 2 methyl groups, or 2 hydrogens, or 2 chlorines, or even 2 halogens. Just something that's common. You compare those on the same side of the pi bond, then it becomes cis. If it's on the opposite side to the pi bond, it's trans. All right. How do you identify cis-trans isomer? Are both groups on the double bond? Are both groups on a double bonded carbon the same? If they are, no cis-trans isomers. Okay. Now this one, look at how this one is. Does this carbon have 2 of the same groups attached? No. Does this carbon have 2 of the same groups attached? No. So you can't have cis-trans isomers. Look for a same group on both sides. There's a methyl group. There's a methyl group. Now we got a cis-trans relationship because we have 2 groups that are the same that we can compare if they're on the same side or opposite sides of double bond. Okay. Does A equal B or does C equal D? Okay. If no, then you can continue. They're not the same. Is one group on each carbon the same? There's our methyl groups. These are the same. So now we can compare them. As long as these are different and these are different, and we have one group that's the same on both sides of it, we can compare them to see if it's cis or trans isomers. Okay, you continue. A equals C, you have a isomer for all the reasons we just said. So this would be cis on the same side. Pentene, there's 5 carbons on the longest carbon chain, which runs down here. So 1, 2, 3, 4, and 5. We have 2 pentene with a double bond, 5 carbons, double bond number 2, and a 3-methyl group attached. And this is in the cis relationship. All right, try again. Number 1 carbon. Does number 1 carbon have 2 different groups attached? Yeah, it has a hydrogen and a chlorine. So those are different. Does the number 2 carbon have 2 different groups attached?
Yes.
Yeah, perfect. One's an ethyl group, one's a chlorine. Okay, when we keep going on, we can have cis-trans isomers. Are there 2 groups attached to those carbons that are the same that we can compare?
Yes.
Yeah.
The chlorine.
Perfect. The chlorines, right? We can compare the chlorines. And what relationship are they in, cis or trans?
trans.
So this is a trans, opposite sides of the double bond. You got it. So this is trans, and then we would name it. This is 1, 2, 3, 4 carbons. So it's butene,
Teen.
double bond carbon. And we have substituents attached, which are your chlorine groups. And they're what numbers?
1 and 2.
1, 2 dichloral. Perfect. So put this whole thing together. You have trans 1, 2 dichloral butene. Okay, substituents are the same. Where are we at? So we went through that. So putting all together, we have trans 1, 2 dichloral 1 butene. Okay. If this chlorine was attached to this carbon, we could not have cis trans isomers because it wouldn't relate to anything different. It'd be the same no matter which way it went. Okay. For the following compounds, decide whether each compound is cis or trans or neither, and give the correct IUPAC name.
I was just curious. It's a mild.
Okay. All right. So could this be cis, trans, or neither? Which one is this? Look at it.
Trans.
That's trans. Okay. Different groups attached to each carbon. They don't have the same. And you have one that's similar. So this is a trans
I'm ready.
relationship. And what's
I
the
was ready.
name of this thing? Let's see. Where's our longest carbon chain?
5.
Yeah, and Tyler's gonna be there late.
Just like that.
anyway, so-
1, 2, 3, 4, 5. Perfect. So this is 5 carbons is
I'm gonna stop and.
Pentene.
pentene. The double bonds at number
So y'all might be getting some snacks.
1, 2.
not 1, 2. Perfect. Number 2, because this is 1, 2, 3, 4, 5. And we have substituent groups. Now we have substituent groups coming off the chain. And that one comes off the chain. So what are the numbers of what we have? 2 methyl groups, right? What are their numbers?
3, 4 dimethane.
By methyl. Perfect.
methyl.
That's all right. 3, 4 dimethyl. So put this together. What will we have? What's the name?
3, 4 dimethyl 2 pentene.
Something goes in front of it.
Trans.
Perfect. So trans 3, 4 dimethyl 2 pentene.
Yeah, that too.
Where's our number? There we go. Trans,
I think I'll stop at some time.
and it's trans 3, 4 dimethyl 2 pentene. Perfect. Sit down, bud. Sit down, Pumps. You're a good boy.
Oh, I'm gonna make, I think I'm gonna
You're a
make
good
brownie
boy.
pops and,
All right.
um,
Here's another one.
velvet pops too.
Okay. Does this carbon
Like cake pops. And they'd be-
have 2 of the same thing attached to it?
Stick all the-
No.
Nope. Does this carbon have 2 of the same thing attached to it?
Yes.
All right. So no isomer. If one of those are the same, no matter how you rotate it, if this switches with this in space, it's the same thing. So if the same thing's attached to one of the carbons in that double bond, you cannot have isomers. So there is no cis trans isomers on this one, but we can still name it, right?
Yes.
So longest carbon chain
5.
is 2, 3, 4, 5. There we go.
Yeah, if I master the tea bag, I'll let you know.
There's 5 carbons. So 5 carbons is
I usually can work with lollipop type stuff.
Pentene.
And- pentene, and the double bond is at number 2. 1, 2,
Oh.
3,
You
4.
probably have to get the right
5.
for that. That's why I was gonna stop the case.
So 2 pentene,
Yeah.
and we have 3 substituents. We have this mess,
I was gonna try
We
to
have
get the
this.
lemon one,
and we have this.
'cause
Now I'll be impressed if you remember all of these. So at number 2,
I'll let you know if I master it.
we have what
I'm
attachment?
pretty confident.
Chloral.
Chloral.
Because I can fix it up in an hour.
At number 4, I have what attachment?
Methyl.
methyl.
I've always wanted to master.
At number 3,
How exciting.
I have what attachment?
Isopropyl.
Perfect. You got it. I'm very good. Isopropyl.
Yes, I did. They should do,
3 carbons with the middle one, iso, being attached.
Maybe of the great bake-off, though.
All right.
What a
So
mere
no cis trans.
great bake-off for two
Alphabetical
days.
order.
Keep looking for it.
And remember, the prefixes don't count for alphabetical order. So this is a P, this is an M, this is a C. So you put it in that kind of order.
Kindle version,
So it would be 2 chloral,
I download on Etsy
4
all
methyl,
the recipes,
3 isopropyl, 2 pentene with no
It's
cis
her
trans.
Bible. It's her Bible.
Okay,
I'm
so
sorry,
it's
how
needed.
come the
No-
isopropyl is not in front of the methyl?
because it's a P. The prefixes don't count.
Okay,
So if you had, yeah, if so, it's iso and propyl is what your number is, the P right there. Okay. Just like dimethyl, the di doesn't count. Tripropyl, the tri doesn't count. What you put in front of the basic carbon structure doesn't count for alphabetical order. Does that make sense?
yes,
Okay, so it'll be the 2 chloral,
Tiny thin ones that you curl.
okay, 4 methyl,
Did you watch the show where they
3 isopropyl.
they're like-
2
they did round
pentene.
eggs and it's a real
Again, so
like
this
top on it, and you spread
right here is my
it,
isopropyl on
over
this.
it, and you let
Isopropyl,
the top take off, and it's like-
okay, that doesn't, that's not considered in alphabetical order. It's the carbon structure that's considered, not the prefix.
okay.
and you swirl,
Okay,
Yep.
that was a tough one.
Tyler has always liked those things that you curl and dip in chocolate.
All right.
He's always liked that, so I thought I'd make some.
Okay, does this carbon
I'd like to get for his wedding.
have 2 different things attached?
Yes,
Does this carbon have 2 different things attached?
yes,
We can have an isomer probably.
Yeah.
So longest carbon chain,
Oh, yeah.
right there. Now,
She loves to- she
what
loves-
isomer is that?
She loves to bake, she can fix sour.
hexene,
What's that?
hexene,
What isomer? Cis or trans?
oh, cis,
Cis. This is cis on both sides. And it's hexene. What number hexene?
Oh, okay, because as soon as I get home, I'll get you out that polyurethane stuff.
Where's the double bond at? What carbon?
3,
3. And are there any substituents?
no,
Nope, those are just
Okay,
hydrogen.
we'll see you tomorrow. All right.
So cis 3 hexene would be the name of this thing. There's your cis relationship right there. Cis 3 hexene. And that's it. That's how you name it. Oops, went backwards. I didn't want to go backwards. Cis 3 hexene, do it this way. All right, 6,3 cis 3 hexene. Okay. 2 isomers of 2-butene are shown below. Which is the cis isomer and which is a trans isomer? Give the IUPAC name for each one. So is the first one here? Is this cis or trans?
cis,
This one's cis. This one must be trans. Everybody see the difference? These are on the same side of the double bond. They both go down. These are on opposite sides of the double bond. One goes down, one goes up. Trans is different or opposite sides. Cis is the same sides of double bond. Okay. And then name it. This has how many carbons?
4,
4. So it's butene, right?
butene,
Okay. And the double bond is at which number?
2,
They're both 2-butene. One cis, one's trans. Okay. Where are we at? There's your relationship, cis, trans. So the one on the left is cis 2-butene. The one on the right is trans 2-butene. All right. Name the following cis-trans isomer. Okay, is it cis or trans or can't or neither?
Trans.
It is trans. You got chlorine on opposite sides. You got alkyl groups on opposite sides. This is trans. Longest carbon chain is
7.
3, 4, 5 is 7. And we're going to number it left to right or right to left?
Top right down.
Right to left. 1, 2, 3, 4, 5, 6, 7. That's how we're going to number it. Everybody see why? To give that double bond the lowest possible number. All right. So, excuse me, 7 carbons is heptene. And what number goes with that?
3.
3 heptene. That's your double bond is. You have 2 substituents of chlorine at 3 and at 4. 3, 4 di chloro. Put all that together. What does that become? What's the official IUPAC name of this compound now?
Trans 3, 4 dichloro 3 heptene.
That's it. Perfect. Heptene, number 3, substituent, configuration is trans. It is trans 3, 4 dichloro 3 heptene. Okay. All right, longest carbon chain again.
8.
1, 2, 3, 4, 5, 6, 7, 8 carbons. Okay, so this is octene. And what's the number? Where's the double bond start?
3.
So it's 3 octene. Okay, are cis-trans isomers possible?
Yes.
When you got 2 methyl groups that are the same.
This.
So this is cis, you're right. This is a cis relationship. Isomeric relationship is cis position. And the substituents are 2 methyl groups.
Exactly.
At what numbers?
3 and 4.
3, 4 di methyl. So you've got your configuration, you got your root name, and you got your substituent. That's it. And you put them together. So here's our parent chain was octene. Position of double bond was number 3. Substituents were 3, 4 dimethyl, and the configuration is cis. So what's the name of this compound on the IUPAC nomenclature?
Cis 3, 4 dimethyl 3 octene.
Got it. Just put, if you work it out just like this, and you put these names together, you get it right every time. Cis 3, 4 dimethyl 3 octene. Cis-trans isomers and name them. Same thing we've been doing. Are cis-trans isomers possible with this structure here?
Yes.
Yes, they are. Okay. What is this? Cis or trans?
Cis.
This is cis. That's good. All right. So this is cis. Our longest carbon chain runs through here. So this is how many carbons?
6.
6 carbons. So it's hexene. And the double bond is at what position?
2.
Number 2. And we have 2 substituents, 2 attachments here. This was 1, 2, 3, 4, 5, 6. Okay. So what's our attachments here?
4, 5 dibro.
4, 5 dibromo. Perfect. So put it together. So this is a cis isomer. So put the name together. What do we got?
Cis 4, 5 dibromo 2 hexene.
You got it. Perfect. Cis, 4,5 dibromo, 2 hexene. Okay. This one here. Okay. Different attachments on each of these carbons here. Has different attachments. We have isomers, something the same. Is this a cis or a trans isomer?
Trans.
It's trans. Bromines are on opposite sides. Ethyl groups are on opposite sides. It's a trans isomer. It is 1, 2, 3, 4, 6 carbons again. 6 carbons is hexene, and it's at the number 3 carbon. So 3 hexene, and it's 3, 4, where your bromines are at, dibromo. So someone put that together. What do we got?
Trans 3,4 dibromo 3 hexane.
Got it. Perfect. We've got trans, 3, 4 dibromo, 3 hexane. All right. Different attachments on each carbon of the double bond. And we got 2 that are similar. So we have a cis trans isomer. Is this cis or trans?
Trans.
This is trans because the 2 methyl groups are on opposite sides of the double bond. So 1, 2, 3, 4, 5, 6 carbons is your chain. Here's your chain. Right. 6 carbons is hex, and it's a double bond. So it's ENE ending. And it's at number 2. This is where the double bond starts. Okay. You have 1 attachment. What is it? What's your 1 substituent here?
Methyl.
Methyl. Perfect. Perfect. Methyl at number 3. Okay. So put this together. What do we have?
Trans 3 methyl 2 hexene.
Perfect. Trans, 3 methyl, 2 hexene. Determine whether each of the following molecules can exist as a cis trans isomer. Okay, what we've been doing. All right. 1 pentene. Can 1 pentene be cis or trans isomer? What you have to do is draw it out and take a look at it. Okay. Five carbons, right? Pentene, number 1, there's a double bond. Hydrogen, 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 CH2, CH2, CH3. So to draw it out, to check the double bond, we'd have hydrogen, bonded to hydrogen, double bond carbon, bonded to hydrogen, CH2, CH2, CH3. That's what we got for 1 pentene. Can that be a cis trans isomer?
No,
Perfect. Perfect. Why? You got it.
because there's 2 hydrogens on the left, so they're not different.
Perfect. That's exactly right. Couldn't have said it better myself. There's 2 hydrogens attached to the first carbon, so it can't be different. If these switch places, it's going to make no difference. So there's no way of having a cis trans isomer for 1 pentene. Okay. Here it is drawn out, just like I drew it. It's a little bit neater, but you see these are 2 of the exact same things that are attached to one of the carbons on the double bond. That means you cannot have isomers. Okay. No cis trans isomers are possible. Does not have 2 different groups attached to the number 1 carbon of the double bond. Okay, how about 3-ethyl-3-hexene? Let's draw that out. Hexene is 6 carbons. Number 3 is a double bond. Number 3 has an ethyl group. Okay. So what we've got is CH3, CH2, bonded to carbon, bonded CH2, CH3. There's your double bond. And another carbon, and then bonded to CH2, CH3, bonded to hydrogen. That's CH2, CH3. Okay, can that have cis trans isomers? 1, 2, 3, 4,
No.
5, 6. No, perfect. Why not?
Because the CH3 and CH2 are on the same sides.
Same thing attached to one of the carbons of the double bond. Impossible to have cis trans isomers. Okay, there's it drawn out. 2 of the same thing. Okay. No cis trans isomers possible. All right, 2-methyl-2-pentene. 5 carbons. And at 3, there's a methyl 2-pentene. There's a double bond. And at 3, there's a methyl group. Okay, so this has CH3 attached to the carbon of your double bond. This one has a methyl group attached. This one has CH2, CH3, CH. Okay, that's right, right? Pentene 1, 2, 3, 4, 5, 2-pentene, 1, 2, 3 methyl. All right, can this one have cis trans isomers?
Cis.
Perfect. Well, I drew it as cis. I could have drawn it as trans too. But yeah, it can have cis trans isomer. All right. I could have drawn it either way. Let me get rid of some of these out of the way so it can be a little clearer here. It's a little neater than me drawing. All right. So here's your 3-methyl-2-pentene. Okay. You can see you have a methyl group here, a methyl group here, and then different groups under there. Methyl group here, methyl group here. So you can compare those. So that's a cis on the left, a trans on the right. So yes, you can have cis trans isomers. Okay. To have cis trans isomers, you have to have different groups on the carbon attached to double bond. And then you have to have a group that's similar that you can compare. And then you have cis trans isomers. So we have this carbon has 2 different groups. This carbon has 2 different groups. And they both have a CH3 group, one that's similar, the same, so we can compare. So yeah, we can have cis trans isomers for that. Right, same thing, cis trans isomers. See what we got. Can that be a cis trans isomer? Anyone want to guess it, yes or no?
Yes.
Okay, there it is drawn out. We draw it out so we can isolate it. You can see where the double bond is. Again, different attachments on this carbon and different attachments on this carbon. And we have something similar. We have hydrogen here and hydrogen here. We can compare. Okay, so this is a trans. And again, hydrogens can be up the top. And that's a cis. So what's the name of the one on the left?
Trans.
Trans what?
2-pentene.
Perfect. Trans 2-pentene. And the one on the right is cis 2-pentene. Okay. So you're, can this have cis trans isomers?
It's neither.
Neither, right? You got two bromines on that carbon. Can't have the same thing. You draw it out. This has the same attachment on one of the carbons. So no matter how you switch this, it's going to make no difference. You cannot have cis trans isomers. Okay. Someone want to name this thing?
One, two, tribromo.
Keep going.
One pentene.
Got it. Perfect. Exactly right. Hey, you can know cis trans isomers, but it said to name it, and it's 1,1,2 tribromo 1-pentene. You name each of the substituents, tell me where the double bond's located, and the longest carbon chain is 5. And no cis trans isomers are possible with that. Are cis trans isomers possible with this one?
No.
No. 2 hydrogens on the carbon with a double bond. Okay. So no matter where we move these up or down, it makes no difference. Not going to change. So who wants to name this one?
One propene.
Perfect. Perfect. 1-propene. Or just propene. Either way is fine. Okay, but no cis trans isomers are possible, but 1-propene. Okay, just a couple more here and we will finish up. All right.
Yeah, I'm ready for my husband.
Consistency, CBR, this one. Draw it out. See what it looks like. Draw the structure. Are cis trans isomers possible?
Yes.
Yeah, perfect. Yes. Look at this carbon. Okay, 2 different things attached. Look at this carbon. 2 different things attached. Is there something similar? Yep, 2 bromines. Okay, so you can draw it either way. You can draw this is what configuration that I've drawn here?
Trans.
Trans. Or we could have drawn it on the same side, and this could have been cis. So this is trans. This one here is cis, and it is. Let's name this thing. There's your longest carbon chain. 6. So this would be trans, and then 2,3 dibromo 2 hexene, right? So trans relationship, 2,3 dibromo, 2 bromos, 1 at 2, 1 at 3, and the E and E, 6 carbons, the E and E double bond at number 2, and the same thing on the bottom except it's cis. 2,3 dibromo 2 hexene.